One of the functional groups we talked about in the previous section was alkenes. Alkenes are hydrocarbons that contain a carbon-carbon double bond. And we name them similar to alkanes, which are all carbons and hydrogen single bonds, but we use the suffix ene instead of ane. We normally indicate the position of the double bond with a number. So for example, if we had the following alkene, this is a 4-carbon chain, and as we count along the chain, the double bond starts at the 2 position. So it's between carbons 2 and 3. And so we say that this is 2-butene. Or we say it's but-2-ene. Where the 2 indicates the position of the alkene along the chain, and the ene indicates that you have a double bond. Now this is different than, say, that alkene, which has the double bond on the 1 position along the chain, and so this would be just simply butene. Or if you wanted to say 1-butene, that would be okay. And when substituents are placed along the chain, the priority rules still must be followed. So alkenes are higher priority than halides, but lower priority than alcohols, for example. So if we had the following structure, this would be a 6-bromo 1-hexene. And this structure would be a 5-methyl hex 4-ene 1-ol. And we say that the suffix is OL because that's the highest priority functional group in this molecule. There are 3 other groups that contain a carbon-carbon double bond which have common names, so we'll go over those right now. The first is the vinyl group. So a vinyl group is just a double bond that's hanging off of a chain. This is known as a vinyl group. So the common name for that molecule would be vinyl bromide. The next common group is this one, which is CH2 followed by a double bond, and this is known as the allyl group. And this molecule here would be allyl bromide. And the last group is this one, which kind of has a branched system, and we know from the isopropyl group that it has the prefix iso, meaning branched. This is an isopropenyl group, indicating that you have a double bond on one of those branches, and so the molecule that has a bromine substituted would be known as isopropenyl bromide. And these are common names for functional groups that contain double bonds. Now, how do we name double bonds for IUPAC nomenclature? Well, it's similar to what we just described before, where you have in the examples on the bottom, 6-bromo 1-hexene or 5-methyl hex 4-ene 1-ol. But there's one additional piece of information, and that's when you have multiple groups on either side of an alkene. And so this is where we get into a convention known as E and Z nomenclature. The E and Z nomenclature of alkenes is also known as the Kohn-Ingold-Prelog convention, and it dictates that we assign priority to the various groups attached to the alkene in order to distinguish between the isomers. So the E alkene, or prefix E, comes from the German word entgegen for opposite, and it's to indicate that two highest priority groups exist on opposite sides of the alkene. Whereas the Z isomer, Z stands for the German word for same, or zusammen. This indicates that the two highest priority groups lie on the same side of the alkene. And the E and Z system of nomenclature assigns priority based upon atomic number. And so there are several rules that we have to follow. The first is that atoms directly attached to the alkene are assigned priority based on their decreasing atomic number. So the higher atomic number is higher priority. Now, if two groups have the same atomic number, you consider atomic mass. So groups that have the same atomic number but higher atomic mass are going to be higher priority. If those two are the same, if two groups have the same atomic number and the same atomic mass, you have to move along the chain to a different atom. Until there's a difference in priority. The fourth rule is that if two groups have the same atomic number and the same atomic mass and lie in the same position along the chain, but one of them is doubly bonded, then you count that atom twice. All right, so if above is the same, you count double bonds or triple bonds multiple times. All right, so let's say you arrive at an oxygen along the chain, but one of them is only singly bonded while the other is doubly bonded. The one that's doubly bonded will count twice. It's as if an atom were attached to two oxygen atoms because it has two bonds. But you have to be careful, this is not additive, so you can't add the atomic numbers of two oxygen atoms. It's just simply that it's doubly bonded. And the final rule states that if the two highest priority groups are on the same side, we say that's Z. If they're on opposite sides, we say that those are E isomers. And this designation goes before the entire name. And so you would have a Z alkene or an E alkene. Now note that we don't use the terms cis and trans when naming alkenes. We only do this because the E and Z nomenclatures are IUPAC conventions. Cis and trans are used only when indicating the relative positions of the groups. So we can talk about them about two groups being cis or trans to one another, but when we name them using IUPAC nomenclature, we have to use Z and E designations. So let's do a couple of examples. So let's say we have the following alkene. The first thing we do is we look to see where the alkene is, and we designate the two carbons of the alkene. Now each of those two carbons should be treated one by one, so let me label them with a different color. Let's treat the red carbon first. On that red carbon we have a methyl group, so that's a carbon atom that's directly attached to the double bond, and then we have a hydrogen atom that's directly attached to the double bond. In this particular case, carbon has an atomic number of 6, while hydrogen has an atomic number of 1, and so the methyl group is higher priority, so I'm going to circle it. Now for the blue carbon, I'm taking a look at the atoms that are directly attached to that blue carbon, and I have carbon atoms in each case. I have a carbon atom there and a carbon atom there. Well, that's the same atomic mass, and so we have to move along down the chain. The next thing we consider is the same atomic, first is atomic number, then atomic mass. We don't have any isotopes here, and so we move along the chain, and now we have an oxygen and a fluorine. Well, this first one here is got 3 bonds to oxygen, a double bond and a single bond, but the fluorine is only single bonded. Now, if you recall what I said before is that when you have double and triple bonds, you count those as if they're bonded twice or 3 times to a particular atom, but it's not additive. So you're still just dealing with a single oxygen in terms of the atomic number. So oxygen's atomic number is 8, but fluorine's atomic number is 9. And so fluorine is the one that is higher atomic number, even though that top orange carbon is bound to 3 different oxygen atoms. 3 different oxygen atoms is not higher priority than a single fluorine because it's based upon atomic number. And so these groups are on the same side, and so this would be an example of a Z alkene. Another example would be this one. Okay, in this case we have that red carbon atom has a methyl group and a hydrogen, and again, the methyl group is going to be higher priority. On the blue carbon, we have 2 carbon atoms that it's connected to, so we have to move along further down the chain. And now we get to oxygens in either case, but in this time, the top orange carbon atom is bound to 3 oxygens, while the bottom orange carbon is only bound to 1 oxygen. And so in this case, the atomic number is the same, but the number of oxygens it's attached to is higher, so that makes the top carbon higher priority, and so this now is an E alkene. They're on opposite sides. Another example would be this one. And so we have the red carbon again. Red carbon still has a methyl and a hydrogen, so that's going to be higher priority for methyl. And now we have a hydrogen and a deuterium on the blue carbon. And this is a case where there's a difference in atomic mass. Both hydrogen and deuterium have the same atomic number, But deuterium has an extra neutron, and so it's going to be higher priority because the atomic mass is 2 instead of 1, and so this is going to be an E alkene. And this is important when naming lots of different types of molecules. Here's just an example of a molecule that has a common name, but we still use the E and Z nomenclature. In this example, the two highest priority groups are going to be that methyl and that carboxylic acid. This is known as E-tiglic acid. The other stereoisomer is going to be this one, and in this case the methyl and the carboxylic acid are on the same side, and this is known as Z, angelic acid. All right, and of course as you have these groups on opposite sides of that double bond, these are known as stereoisomers. They have the same constitution, but a different orientation in space. Now these stereoisomers that arise from a difference in E and Z for alkenes are a specific type of stereoisomer known as a geometric isomer. So stereoisomer is sort of the bigger umbrella, and underneath stereoisomer is a smaller umbrella called geometric isomers. And this geometric isomer class is a class of stereoisomers known as diastereomers. And we'll get to that term diastereomer in the next chapter on stereochemistry. Now these geometric isomers, these diastereomers, do not have the same physical properties because they have different energies. And we can see that actually in the isomers of butene. So let's take a look at butene. And so butene has the following two isomers. We have an E-butene. This is E2-butene. But we also have the Z version, Z2-butene. These are different molecules. They are geometric isomers of one another, but they are indeed different molecules, and they have different physical properties because they have different energies. It turns out that the E isomer is about 0.7 kcals per mole more stable. And the reason why this is more stable is because it has those two methyl groups on opposite sides of that double bond. And so in the Z2-butene, you have a van der Waals interaction when those two methyl groups come into close contact with one another. And those two methyl groups are lying cis along that double bond. This increases the steric strain of the molecule ever so slightly that it's higher in energy. It drives up the energy of that cis isomer. Another way of depicting this is if we were to draw out the hydrogen atoms of that methyl group. So let's do that. We see, just like in the case of conformational analysis, when we have the nuclei of two atoms overlapping, that gives rise to an increase in steric strain. And so we know that the E isomer and the Z isomer are going to be different in energy. Why do alkenes exhibit this stereoisomerism in the first place? Well, you have to remember that the molecular orbital description of a CC double bond involves the formation of a pi bond. So let's take a look at that. So bonding, stereoisomerism, and stability. Remember that the carbon atoms of an alkene are sp2 hybridized, which means that each carbon atom has 3 sp2 hybridized orbitals and 1 atomic p orbital. So if we were to take a look at ethylene, which is the simplest alkene, there's going to be net bonding in between the two carbon atoms, the sigma cc bond, and you're going to have a pi cc bond that's above and below the plane of the molecule. So let's build that out. So we have a carbon atom that has an sp2 hybridized orbital here, an sp2 hybridized orbital that's sitting in back, an sp2 hybridized orbital that's coming out towards you. This is a trigonal planar atom. And then we have an atomic p that's above and below the plane. And so we have 1 electron in each of those orbitals. Now, if I wanted to describe the bonding in between the two carbon atoms, I would ignore the bonds that are made to each of the hydrogens. I'm going to draw in the other carbon on the other side. Add in a bunch of electrons. And again, I ignore the two that are made to hydrogens on either side. And what I see is that a new head-on overlap between sp2 hybridized orbitals will give rise to a sigma bond, a sigma cc bond, that has 2 electrons in it, and a sigma star cc with no electrons in it. This is a symmetrical molecule, and so the cc sigma bond would look something like this. And there's a node in between the two carbon atoms for the sigma star cc. Now we also have sideways overlap, or above and below the plane overlap, between the atomic p orbitals of those sp2 hybridized carbons. And so that's going to give rise to a pi and a pi star. The pi bond is going to have bonding above and below the plane. And then in the antibonding orbital, the pi star, you're going to have bonding above and below the plane as well. You're going to have electron sink, above and below the plane. And as you cross the nodal plane, you're going to change the phasing. There are 2 electrons in that pi cc bond, and so there are 4 electrons total in the cc double bond. 2 are in the sigma cc, and 2 are in the pi cc. Now, another thing that's important about this molecular orbital description is that the reacting orbitals are sometimes known as the frontier molecular orbitals. The frontier molecular orbitals are the reacting orbitals. These are the ones that are going to be involved in chemical reactions. And so there are 2 orbitals that we worry about for alkene systems. The first is known as the HOMO. And the HOMO stands for the highest occupied molecular orbital. And if we look at our molecular orbital description for the molecule ethene, or ethylene, we see that the highest occupied molecular orbital, meaning it has a pair of electrons in it, is the pi cc bond. So the pi cc bond is the HOMO in ethene. The other orbital that we care about, the other frontier molecular orbital we care about, is the LUMO. This stands for the lowest unoccupied molecular orbital. And the LUMO in ethylene happens to be the pi star CC. So the HOMO is the highest occupied molecular orbital. It's higher in energy than the sigma CC. The pi CC is higher in energy than the sigma CC. So it's the highest energy pair of electrons we have, and it's the one that's going to be used if we take ethylene and we react it with something else. We don't want to take electrons that are lower in energy. We want to take electrons that are higher in energy and react them. Likewise, if we take the molecule ethylene and we want to accept a pair of electrons into this molecule, we need to accept that pair of electrons into the lowest energy orbital that we can. We don't want to take a very, very high energy orbital. We want to take a low energy orbital to accept a pair of electrons. And so the lowest energy molecular orbital that we have is the pi star CC, which is lower in energy than the sigma CC. And so these two orbitals are going to be important as we move forward. The HOMO in the case of an alkene is always the pi CC, and the LUMO in the case of an alkene is always the pi star CC. Now, a double bond increases the strength of a carbon-carbon bond by 62 kcals per mole. So a sigma CC bond has a bond strength of 83 kcals per mole. But a double bond, right, has a bond strength of 145 kcals per mole. Okay, so this is a single sigma CC bond. Now a double bond is the combination of a sigma CC plus a pi CC. And so we can see here that the difference is about 62 kcals per mole. And so we see that the pi CC bond is not quite as strong as a sigma CC bond, and this is the reason why it's slightly higher in energy. Now, because there is net bonding above and below the plane, there's no longer rotation about that central CC bond, and so we create stereoisomers. And so if we have our two examples again, the two methyl groups on the same side versus the two methyl groups on the opposite side for butene, we see that the bond rotation around here is not possible. And so this creates stereoisomerism about that central CC bond. Thus we have these isolable isomers. Now, one other important feature of alkene is their relative stability. Alkenes that are more highly substituted are more stable than less highly substituted alkenes. Okay, so if we have a simple monosubstituted alkene, there's only one substitution on it, this R group. We say that this is the least stable of the following series that I'm going to draw. We have several different types of di-substituted systems. We have the 1,1 di-substituted, we have the 1,2 di-substituted, that's cis, and the 1,2 di-substituted, which is trans. So these are di-substituted. we have the tri-substituted, and then finally we have the tetrasubstituted. And the tetrasubstituted are going to be the most stable of this series. And so alkenes that are more highly substituted, the tri and tetrasubstituted, are more stable than less highly substituted alkenes. Now, what is the reason for this? The reason for this is sigma donation. And so we need to take a look at the forces that are going on in alkenes to consider why it is that more highly substituted alkenes are more stable. So what we kind of need to do is to look at two different alkenes and compare them. So we want to compare the example of propene with dimethylpropene. So I'm going to draw those out. So here's dimethylpropene, and over here I just have simple propene. Now, we should know from the mnemonic that I just gave you that the di-substituted is going to be more stable than the monosubstituted. So dimethyl propene, the dimethyl case is more stable. We say that the greater substitution on this molecule stabilizes this molecule. And it does this through sigma donation. Now, stability is an important phenomenon. So stability is really the sum of all the bond enthalpies. So it's really the sum of all of the sigma and pi bonds that you have in a molecule. So for the more stable species, this 2-methyl-1-propene, we have some additional sigma bonds in this molecule. So what's the effect of having these additional sigma bonds? Well, let's look at the molecular orbital description. I'm going to take that that pi cc bond and kind of rotate it a little bit so that it's coming out towards you. So I'm going to have a hydrogen coming out towards you here, and a methyl group, hydrogen going back, and then a methyl group kind of pointing out towards you, and a methyl group kind of pointing away from you. Okay? Now, in this particular orientation, we need to consider where we have sigma CH bonds, because those are the things that are going to perform sigma donation. We have a sigma CH bond right here and right here. So those two sigma CH bonds would want to delocalize. Now, where could they delocalize into? Well, there's an orbital nearby, and it happens to be the pi star cc. So here's the pi star cc, and the electrons that are in the sigma CH bond are actually delocalizing into that pi cc, both on the methyl group on the bottom and the methyl group at the top. Now let's take a look at the 1-propene case. We still have an orientation of this molecule in which we've got the two hydrogens going either towards you or back away from you, and then we have a methyl group that's pointing towards you. we still have sigma CH pair of electrons. We still have a pi star that it could delocalize into. But the problem here is that there are half as many of these types of sigma donations. If you look at the 2-methyl-1-propene, you can actually do this 6 times. And the reason for this is that you can get each one of those sigma CH bonds to rotate around that carbon-carbon bond, and at any one point, each of those CHs is overlapping with the pi star CC. But over here on the other example, you only can do this 3 times for one propene. Right? Each of those CH bonds rotate, but the hydrogen atom here is not performing sigma donation because it doesn't lie above and below the plane where the pi star CC does. And so what happens is we say that there's more stability for the sigma the 2-methyl-1-propene. Now, how do we know that this is the case? We can take a look at the overlap between a sigma CH pair of electrons with a pi star CC antibonding orbital. So we have 2 electrons here. Let's say we overlap those 2 orbitals. They will create 2 new molecular orbitals. Those 2 new molecular orbitals will be a new sigma CH and a new pi star CC. We have 2 electrons in that sigma CH, and so what happened overall, the delocalization of those sigma CH electrons into the pi star CC drove down the energy of those sigma CH pair of electrons. Because you have more of these diagrams in the case of the 2-methyl-1-propene than you do 1-propene, you have 6 of these diagrams versus 3 of these diagrams. Overall, the sum of the bond enthalpies will be lower for 2-methyl-1-propene. Okay, so if you have additional sigma donation, that will give rise to more of the sigma CH electrons being able to spread out over greater distances, and this, of course, leads to greater stability because the sum of the bond enthalpies will go down. Now, there are a couple of other considerations when we are dealing with stability of alkenes. It's not only that more highly substituted alkenes are more stable, but we sometimes have alkenes inside ring-like systems. So besides steric strain and sigma donation, alkene stability can be affected by ring strain. Placing a double bond inside a ring alters the conformation of that ring and contributes to angle strain. And so if we have the following series, we have cyclopropene, cyclobutene, cyclopentene, and cyclohexene, we see that there are fewer degrees of freedom in the case of the cyclopropene and the cyclobutene. And so these 2 molecules are highly strained because it's trying to force the double bond to have some weird geometries for the carbon atoms. So these 2 carbon atoms right here are forced to be 60 degrees when they really want to be 120 in terms of their bond angles. But the cyclopentene and the cyclohexene don't suffer from this kind of angle strain, even though there's a little bit more, little fewer degrees of freedom for these molecules. There isn't quite as much ring strain for these molecules because they're slightly larger. And so these alkene carbon atoms that are sp2 hybridized want to have bond angles of 120. But when they're placed in a ring, sometimes they're forced to be much smaller than that. And so this increases the energy of the cycloalkene. So they're highly strained. The HOMO, in this case, will be higher. Now, larger rings, so if you have a 7 or 8 or 9-membered rings, they don't suffer from angle strain in the opposite sense, where they have greater than 120 bond angles, because the ring can actually distort its conformation to keep the alkene at 120 degrees. And this is actually demonstrated in a couple of the larger cis alkenes. So larger transalkenes. All of these first examples are cis cycloalkenes. And it turns out that you can't really have trans cycloalkenes with rings of this size. It just doesn't fit. The smallest type of trans cycloalkene you can have is cyclooctene. And cyclooctene looks like this. And it actually isn't flat. It's not completely flat. It actually puckers. And so, as I said, these rings don't suffer from angle strain in the opposite sense because the ring can distort its conformation. And it actually does. And it's not flat. It kind of has a conformation that looks like this, where that double bond is kind of sitting in front of one of the pi bonds. And so the smallest trans-cycloalkene system is cyclooctene. Anything smaller than that is just too strained. And the final thing we have to worry about is a rule known as Brett's rule. So Brett's rule states that you can't have a double bond on a bridgehead carbon. So no double bonds on bridgehead carbons. The reason for this is that there's no overlap of atomic p orbitals to create a pi cc bond. And so let's say we had the following example. And so let's say we had this alkene here. Now I just said that you can't have a double bond on a bridgehead carbon. But what would have to happen in order for this to occur? Well, we'd have to have two sp2 hybridized carbon atoms on your bridgehead and the adjacent carbon. And so let's say we dealt with that carbon atom right there. That carbon atom would have to be sp2 hybridized, which would mean it would have 3 sp2 hybridized orbitals plus an atomic p. The atomic p would lie above and below the plane like this. Now on the bridgehead carbon, this green carbon, we would have another sp2 hybridized orbital, sp2 hybridized atom with 3 sp2 hybridized orbitals plus an atomic p, but this time the atomic p is coming out towards you and then back away from you. And so in this particular case, there's no net bonding between those two orbitals. You can't get those electrons that are in those atomic b orbitals to mix. And if they don't mix, they cannot make a pi cc bond. And so we say that these two are orthogonal to one another. These are orthogonal atomic p orbitals. They are basically perpendicular to one another, and there's no net bonding between the two. And so because of that, you cannot have double bonds on bridgehead carbons.